Hello, my name is Mike Heap, and I will present a recent collaborative and multidisciplinary study on the influence of hydrothermal alteration on volcano stability, using La Soufrière de Guadeloupe as an example. Volcanoes are inherently unstable structures that spread and frequently experience mass wasting events such as slope failure, rock falls, and debris flows. Hydrothermal alteration, common to many volcanoes, is often invoked as a mechanism that contributes significantly to volcano instability. For example, motivated by intensive alteration on the flanks and summit of Mount Rainier, Reed et al. Examined the influence of alteration on volcano stability using a geotechnical 3D method of columns limit equilibrium slope stability analysis. Using a best estimate distribution of the alteration and typical values of cohesion, friction angle, and rock unit weight for fresh, lightly altered, and highly altered rocks, these authors found that steep slopes and large volumes of altered and weak rock can promote potentially large gravitational failures. Although studies have improved our understanding of alteration-induced volcano instability, the shape and size of alteration zones and/or the rock properties used in the model are commonly poorly constrained or even assumed. Indeed, there are few mechanical data for variably altered volcanic rocks to inform large-scale volcano modeling. La Soufrière de Guadeloupe, a hazardous andesitic stratovolcano, can be found on the Caribbean island of Guadeloupe. There have been 6 phreatic or hydrothermal eruptions since 1635, the most recent of which, in 1976-1977, was the largest and resulted in the partial evacuation of the island. The volcano has a history of partial collapses, the deposits of which are dominated by hydrothermally altered materials, highlighting the link between alteration and instability. Volcanic unrest, monitored by the observatory, has increased over the last decades. Rock blocks were collected from different sites around the volcano, shown in the map on the left. In total, 17 blocks were collected. The majority of our samples were collected from the collapse scar of the 2009 landslide, shown in the photograph on the right. The rocks exposed by this landslide were considered to best represent the altered lithologies found within the dome. The blocks collected were variably altered andesites. The mineral contents and microstructure of these blocks were investigated using X-ray powder diffraction and scanning electron microscopy. An example SEM image is shown on the right, together with a photograph of one of the samples prepared for the laboratory experiments. XRPD found a mineral assemblage indicative of acid sulfate alteration. The most common alteration minerals were kaolinite, cristobalite, and allanite group minerals. The experiments performed for this study were uniaxial deformation experiments, the diagram on the left, and triaxial deformation experiments, the diagram on the right. These experiments were required to understand the influence of alteration on rock strength and to provide parameters for our large-scale modeling. Here are the results of the uniaxial compressive strength experiments. The diagram on the left shows representative stress-strain curves for select blocks. The mechanical data are summarized in the graphs on the right, which show uniaxial compressive strength and Young's modulus as a function of porosity. Each point represents an experiment performed on an individual cylindrical core prepared from the 17 rock blocks collected. Our results show that uniaxial compressive strength and Young's modulus both decrease as a function of porosity. Important to this study is whether alteration reduces the strength of andesites forming the dome at La Soufrière de Guadeloupe. The graph here shows uniaxial compressive strength as a function of alteration ratio, the ratio of altered to primary minerals in each block as exposed by the X-ray powder diffraction analysis. The porosity of each sample is indicated by the color scale, where yellow represents high porosity and red represents low porosity. These data show that strength decreases as a function of hydrothermal alteration. The relative weakness of the two outliers, samples H20 and H14, can be explained by the high porosity of sample H20 and the presence of mesoscale fractures within sample H14. Triaxial deformation experiments were only performed on 3 blocks, chosen to represent slightly, moderately, and very altered rocks at La Soufrière de Guadeloupe. The graphs provided here show stress-strain curves for samples of each block deformed under different effective pressures, indicated by the number next to each curve. Experiments at different effective pressures were required to calculate cohesion and the internal angle of friction, parameters required in our large-scale flank stability modeling. We find that increasing alteration reduces cohesion but does not systematically influence the internal friction angle. We combined our laboratory data with geophysical data to perform 2D numerical flank stability modeling. We used recent electrical conductivity data, shown in the top image, to create our 2D cross-section, shown in the bottom image. Our simplified north-south cross-section contains 2 regions, a non-deformable region shown in white and a deformable region shown in grey. The deformable region was further split into 2 zones, a moderately altered zone shown in light grey and a highly altered zone shown in dark grey. These zones were characterized by different rock physical and mechanical properties as guided by our new laboratory data. Hydrothermomechanical modeling called LAMEM, which models the non-linear visco-elastoplastic deformation of rocks, was then used to perform the numerical modeling. Here's an example of one of our numerical model runs. The color of the surface represents the surface velocity, where red and blue are high and low velocities respectively, and the color of the deformable domain represents the strain rate. As the model progresses, you can see that a high strain rate slip surface develops, which causes the sliding of the southern flank. In total, we performed 8 model runs. Models were performed using 3 different cross-sections, one representing a homogeneous volcano, one representing the present-day volcano in which the structure is guided by the recent electrical conductivity data, and one in which we artificially increase the size of the highly altered zone to explore the influence of increased alteration on the stability of the volcano. These different scenarios can be seen as thumbnails on the left of the diagram. Models were run on these cross-sections using laboratory-scale mechanical properties and mechanical properties that were upscaled to the scale of the rock mass. Comparing the laboratory scale and upscaled models, we can see the importance of using upscaled values in large-scale modeling. Indeed, the strain rates predicted by the upscaled models are much higher than those predicted by the laboratory scale models. If we focus now on the upscaled models only, we can see the influence of hydrothermal alteration on volcano stability. First, the strain rates within the homogeneous volcano, a volcano without a hydrothermally altered interior, are very low. When we introduce the highly altered zone, guided by the recent geophysical data, we can see that a high slip strain rate zone appears that results in the sliding of the southern flank. If we artificially increase the size of this hydrothermally altered zone, the bottommost diagram, we can see that the strain rate within the flank is much increased. We conclude therefore that hydrothermal alteration decreases volcano stability, and as a result, and due to the hazards posed, we encourage that the extent and evolution of hydrothermal alteration is closely monitored at volcanoes worldwide. Thanks for your attention.